Okay, thanks, Nadi. And thanks organizers for inviting me here. It's always great pleasure to be in IS, especially it's a very exciting summer school. So I'm going to talk about some recent works in mixed-state quantum phases. It's a pretty big title, so before diving in, so first, here are some references that contain results relevant for this talk. And let me start from acknowledgement. This work would not be possible without the wonderful collaborators that I'm fortunate enough to have. Leo, a student in Parameter, Ruochen and Jianhao, they're in the audience, so any difficult questions should be deflected to them. And Tyler is a postdoc in Yale, but we can see that he's going on some complicated trajectory. And Zhen and Chong. Okay, so this is a brief outline of the talk. So I'll start with some motivation and sort of a general discussion of what this problem is about and why we're interested in this problem. And I'll discuss three specific results. One is about what's so-called strong to weak symmetry breaking. And then I'll continue to talk about two examples of exotic or intrinsically mixed state topological phases. I'll try to quantify what these words mean. And just to kind of get everyone interested, to show that there's some interesting things that happen in interesting many-body phenomenon that we encounter in the world of mixed states. Okay, so just to motivate the problem, well, here put in your favorite many-body states. If you are like me, I like topological order states. If the same for you, then we are good friends. So it has a very entangled ground states supporting interesting excitations, etc. Okay, but of course, when we look at this picture, usually we have in mind of the ground state of some Hamiltonian, and we are talking about an isolated system, well isolated from the environment, so you can talk about the ground state, okay, or thermal equilibrium. All right, so this is sort of the spherical chicken in the vacuum, but in reality, you have all kinds of disturbances from interactions with the external environment, with the rest of the universe, right? You can have dissipation, you can find temperature disorder, or just some kind of decoherence that takes place in the system. Okay. All right, so we have to face the reality and think about what happens in an open quantum system. So now there's a kind of a very natural question that to what extent our understanding of topological phases or phase of matter in general in pure states, okay, we have a pretty good understanding of at least some part of that landscape of phases extend to mixed states. Okay, and this has been a very active field, moving very fast. Here's a partial list of references that are mostly dated in the past couple of years, and the list is growing very quickly. So let me now get to some more concrete discussions. Okay, so let's first quickly review what we mean by even phases in the case of pure states. And this is most well understood when we have a topological phase, meaning that we have no ground state of some gap local Hamiltonian. So this is the case where we understand everything most clearly, I would say. Okay, so which states? Which states are we talking about? Of course, here I should say that phases, we can talk about phases when there's no gap, but let me restrict to the case when we understand everything the best. Okay. All right, so let's say we have a ground state of some gap local Hamiltonian. And from these conditions, we also without proof, but it's well established that you have short-range correlations between local operators. Okay, so the state is short-range correlated. So these are the states that are of most interest in this discussion. And we can put on some sort of equivalent relation. We can divide the wild world of many-body states into different phases. In each phase, there's some way to connect one state to another, and that connection is facilitated by adiabatic evolution or in language of quantum information, in terms of a quasi-local quantum circuit, okay? Which is just kind of a model for adiabatic evolution. So if two states can be related to each other via quasi-local circuit, no, this is, without giving you a definition, this is just a circuit that respects the locality of the system. And a simple model for that is just this kind of a brick wall picture of a unitary circuit. If two states can be related this way, then we say they're in the same phase. Okay? And this equivalence relation defines what we mean by phases. And then we can talk about trivial phases, trivial phase, which is the unique phase connected to a product state. And then there are various kinds of non-trivial phases. So to go from one point here to another point, you have to cross a phase transition where the gap closes. Okay, so this is our usual notion of phases in ground states. All right, so now, with that in mind, let's now consider mixed states. So here's just a few facts about mixed states. So in general, mixed states arises because we want to take into account the coupling between the system that we are studying and the environment. Okay. And there are some examples, well-known examples of mixed states. Gibbs states, of course, the thermal state is a mixed state. And you have steady states of some dissipative evolution, or you can just consider in general some quantum states, pure states under subject to some noise or decoherence. Okay. So these are not mutually exclusive, they are overlapping, but these are physically well-motivated examples of mixed states. Now, this is what I actually want to show by saying like a few properties of mixed states. So generally, a quantum state is represented by a density matrix. So mixed states are represented by density matrices, which are Hermitian and positive semi-definite operators with a unit trace. In the case of pure state, this rho is just a projector to a pure state. And in general, you can think of the rho as an ensemble of these states, or pure states. Okay. And a useful fact is that any mixed state can be purified into a pure state, meaning that you can always think of it as a subsystem of some pure state. Okay. Another useful fact that we can make probabilistic mixture of mixed states, meaning that we form a convex sum of density operators, you still get another density operator. Okay. So the space of density operator is a convex set. And this is what I mean by a convex sum. Okay. So basically just a probabilistic mixture of different states. All right, so these are the states, these are the mixed states that I'm going to study. Now, what's the generalization of the equivalence relation in the case of ground states? In that case, we have local unitary evolution. So what replaces this notion of Lewis unitary? Well, so in general, for mixed states in the open quantum system, the evolution is not unitary. The evolution is dissipative, and they can be modeled by quantum channels. So quantum channels, they are just completely positive trace-preserving maps acting on operators. So they map mixed states to another mixed state. To make it a little more clear, let's consider a class of quantum channels where we are talking about many-body systems. So it's not just a quantum mechanical problem. We also want to keep track of locality in the problem. So I'll focus on this class of quantum channel that's called a quasi-local quantum channel. And we can think of any quasi-local channel as composed of 3 steps. Okay? First, I have this pictorial representation of my mixed state. So this is a state, and these legs represent the physical, the bra and cats, right? The basis of bra cats. It's kind of like a tensor network picture. Okay? But of course, I'm not assuming that this is a tensor network, it's just to represent the density operator. And then we introduce some ancilla, which models the environment. Okay? And the ancilla is assumed to be in the product state. And then we allow the system and ancilla to interact, and the interaction is modeled by a quasi-local unitary between the system and ancilla, so they are coupled and entangled in some way. And once we allow the system, the environment to interact for some time. We turn off the interaction, then get rid of the ancillas, and we're left with another mixed state. So we trace out the ancilla, and this way we get a quantum channel acting on the mixed state. Okay. So this is the definition of a quasi-local unitary, quasi-local quantum channel. If you remove all of these locality requirements, this is the most general form of quantum channel. Oh yeah, so the ancilla, of course, has to have the same geometric locality of the system. Right? And we start from a product state in ancilla. And also the interaction between them is local. So every step in this composition, in this kind of description, has to respect locality. All right, so this is the notion of a quasi-local channel. And once we have states, we have a sort of a generalization of evolution. We can start talking about which state should be considered as related to another state, as equivalent to another state. And now, before discussing that, let me just give you the example of what it looks like to have a quantum channel applied to many-body states. Okay, so let's suppose we have a system of n qubits, maybe arranged in some lattice, let's say in a 1D chain, and x and z will represent Pauli operators. So I'll use that convention throughout the talk. And here's an example of a local quantum channel. I didn't represent it as in terms of coupled to environment and traced out environment. I write it in terms of cross operators. So it's a product of channels acting on each side. And on each side, we have a cross operator, which is a Pauli X. Okay? And when you apply this quantum channel to the state, you can expand this into a very large sum. If you look at what happens in each term, well, this one is like applying X to the state with some probability. And this one is applying 2X to the state, again with some probability. Okay? So what we get is a convex sum, a probabilistic mixture of local unitary deformations of rho. Okay? So I'm not saying that this is the most general picture that you get, but this is a kind of a useful mental picture to have. All right, so now let me give a definition of a mixed state phase. So before that, let me say that this is not the unique definition. There are other definitions on the market, but this is one that I would say naturally generalizes the notion of phases in the ground state. So here, the equivalence relation is basically given in terms of the connectivity by quasi-local quantum channel. So if two states, ρ1 and ρ2, two mixed states, belong to the same phase, if we can find, now here's an important difference, we can find two channels, N12 and N21, such that N12 takes 2 to 1, and N21 takes 1 to 2. Okay. So the important difference here is that because quantum channels are not invertible in general, we have to demand connectivity in both directions. All right, and then we can hope or we expect that we get different phases in the landscape of mixed states, many-body mixed states. Okay. All right, so here, just to add a remark that it's essential to have two-way connectedness, because otherwise, if you demand one way, it's not even an equivalence relation. Okay? And second, there's this curious fact that that surprised me first when I thought about this, when I heard about this. But of course, we know because of we know like in thermodynamics or in STEMAC, we know everything is going to become boring if you don't do something about it, right? It's going to turn into a trivial state in the end of the day. And formally, the statement that you can always turn any mixed state you like into a complete boring product state by applying a local quantum channel. It's essentially just introduce the environment, the product state, swap the system with the environment, and that's a legitimate unitary. So you get a legitimate quantum channel, and this is represented pictorially here. This is a state of a system. This is a product state environment, and we just swap them. And now you trace out the environment. You get a trivial state. So you can turn any state into a trivial state. Doesn't mean that they are equivalent, right? We don't want to claim any state is trivial. So that's why we need really to have a two-way connected. The non-trivial questions, can you go back to rho by applying another quantum channel? Okay. Yes.
As local?
Yeah, so the channel is local because I can just apply a swap gate to every qubit. And that's completely local. It's a tensor product of local unitaries. So this is a local channel. All right, so now at least, yes.
So for pure states, for gap pure states, there's this notion of not closing the gap. We connect them. Is there anything that transfers over with this gap closing for mixed state?
Yeah, so in order to discuss questions like gap, we need to have some notion of dynamics. Okay, so in that case, I would say you can discuss similar questions in the context of if you have a concrete dissipative evolution given by for some Lindebladian, okay? Master equation, and then you can talk about gap in that context. So here. What we have is more or less like an evolution of a Lindebladian, which is gapped, at least during this time frame, and for a time that is not too long. Okay, the time should not scale linearly with the system size. We can probably drop the condition gap, but I think that's an intuition.
Like the kind of phase diagram.
Mm-hmm.
Because the line separating the phases.
Mm-hmm.
What do you expect of the line?
So we expect on this line, the states will develop some sort of long-range correlation. Okay, I have to put everything in quote. And I don't think we have a very general understanding of what these transitions are, but there will be example. And I'll probably say a couple words about it. Yeah.
Whether you're restrict with a multi-local unit, it could be finite depth quantum circuit.
So yes, definitely finite depth quantum channels are quasi-local, but I don't want to just have finite depths. It's important to include log depth circuit in order to if you only include finite depth, then certain states which should be connected would not be connected. So we need to allow Pauli log depth circuits. And that's essential. Yeah.
Pure states, we have robustness to perturbations, right? So here, if we have a noise that, let's say, trivializes one state, and because we're imposing two-way condition, then these two are inequivalent, but the state might get trivialized anyway because of the noise, right?
The state can get trivialized by the noise, that's right. So so I think you are suggesting there's a different notion of phases which takes into account the stability under local perturbations in the noise channel. And that's definitely a valid question. And we can think about stability of phases. But here, I'm merely asking what are the different phases under this equivalence relation. The stability is, I would say it's very important, but a slightly different question. All right, so now let me continue. So how do we think about this problem? Well, just like in the case of ground states or any other problem in many-body physics, symmetries are extremely useful tool to sort of anchor our understanding of many-body states. So here, there's an interesting refinement of the notion of symmetry in the case of an open system. Okay? And the refinement is not entirely new. I mean, we know about it in undergraduate, maybe for some of you high school, or when we learned about STEMAC, and we're just kind of lifting that notion to more general open systems. So I want to define two kinds of symmetries. One of them is called weak, the other one is strong, for a good reason. One of them is weaker than the other one. But let me first formally define it, and then I'll say where they come from. So the weak symmetry is just some operator, unitary operator, that commutes with the density matrix. Okay, so W is a symmetry operator. Rho transforms under W into W rho, W dagger, and we say they are equal if we say the rho has a weak symmetry, W if this is the case. Okay. So we can go to a basis where W is diagonalized because rho and W commute. We can diagonalize both of them. And we get a decomposition of rho into pure states with some probability P. And the weak symmetry means all of them are eigenstates of W, but with different eigenvalues. Okay. Now, what's example of weak symmetry? Well, we have one, again, from Stamek. That's a grand canonical ensemble, where the particle number conservation is a weak symmetry because we allow fluctuation of particle numbers in the system. But if you consider both system environment, it's a conserved, particle number is conserved. So we can represent the density matrix, the thermal grand canonical ensemble, as a convex sum of states with well-defined particle numbers. Okay. And more generally, weak symmetry is when you have system plus Bass to preserve the symmetry. But if you look at system alone, its symmetry is not preserved. Right, so if we have weak symmetry, we always have strong symmetry. And strong symmetry acts on density matrix in a weird way. I mean, we don't usually think about action of symmetry on the operator in this way. It's acted only on by one side. So W times rho equals some phase vector times rho. Okay? And this kind of symmetry means that if you form the convex sum of, if you decompose rho into the convex sum pure states, then each one of them has to be eigenstate of W with exactly the same eigenvalue. Okay? And the Stamek example of strong symmetry is canonical ensemble, where we fix the number of particles in the system. We don't allow the particle number to fluctuate, and that's example of a U1 strong symmetry. Okay? So the symmetry is preserved alone, already on the system alone. Okay? You don't have to take into account the environment, it's already a symmetry on the system. Okay, so the fact that you can get a phase vector means strong symmetry is actually very strong. It allows us to keep track of the projective phases, which are important in thinking about questions like anomalies. And if you have a convex sum of density matrices, which has a strong symmetry, then each single one of them has to have the same strong symmetry with the same eigenvalue. Okay? And another property which you can prove using a few lines is that strong symmetry can be sort of commuted through a quantum channel. So it's a very useful tool to study what happens to a state under a quantum channel. Okay. All right, so just to justify why strong symmetry is actually very, very strong. It allows you kind of keep track of quantum mechanical properties of symmetry. Okay. While none of these is true for weak symmetry. All right, okay, so we have all the ingredients. Now we can start doing some many-body physics. So, we have our beloved Landau paradigm. Right? In the old days, that's how we think about phase of matter, even nowadays. So, phase of matter are classified by the global symmetries and how they are spontaneously broken. That's a Landau sort of Ginsburg-Landau way of thinking about phase of matter. Okay? And now with this notion of strong and weak symmetries, we can state it a little more precisely. So the classical Ginsburg-Landau, if you really think about it this way, as quantum Stamek and density matrices, it's about spontaneously breaking a weak symmetry to no symmetry, or maybe a subgroup of that weak symmetry. Okay. What about quantum? Ginsburg-Landau in quantum systems, well, it's most of the time about having a strong symmetry to begin with, and then it's broken to a subgroup or nothing. Okay. But if you look at this list, there's now a distinct possibility in mixed states. That is, you can have a strong symmetry spontaneously broken to just weak symmetry. So I'll call it SW, strong to weak symmetry breaking. And I'll try to explain what this means. All right. Okay, so before we discuss strong to weak symmetry breaking, let me first just review the pure state SSB. Okay. Well, let's use our example of qubits. You have a system of qubits, and the simplest global symmetry you can imagine is a product of Pauli X, so it's a Z2 global symmetry. It's a product of spin flips. And then the SSB state, the representative SSB state is the GHZ state or the CAS state, where we just have a superposition of all spin up state with all spin down state. Okay, this is a CAS state. So this is how we usually write the state, but we can also write it in the X basis. So this is up and down. I forgot to mention up and down are the eigenstates of Z operators. So this is written in Z basis, but we can also write it in the X basis. And then if you write it in the X basis, you actually get a huge superposition of all possible bit strings of X. Little x are eigenvalues of the Pauli Xi on site I. I can have 1 minus 1 minus 1, whatever pattern you can come up with, subject to the constraint that all the products of all of these little xi should be 1, because we start from a state which has eigenvalue 1 under the spin flip. Okay, so we have to respect that global constraint. Okay, but that's the only constraint. Otherwise, you form a superposition of all possible configurations of Z2 charges. So when I say Z2 charges, I mean a site with little xi equals -1. Okay, and this state has long-range order. If you calculate two-point function of order parameter, which is a z, we get exactly 1 in this state. And we can kind of pictorially think about it as a condensation, the Bose-Einstein condensation of the symmetry charges, and that's really exemplified by this way of writing the wave function. Okay, you have superposition of all possible arrangement of charges, and the only constraint that the global symmetry has to, the global quantum number has to be respected. Okay, so it's a coherent condensation. Now, what is the analog in mixed state? Well, so instead of forming a coherent superposition, we can form an incoherent superposition, incoherent mixture. So both of them should be in quotes, incoherent condensation of charges, in the sense that we simply form a convex sum of states with different arrangements of charges. Okay, so it's a convex sum. There's no coherence between them. And if you look at this, it's really just 1 plus x. It's a projector to x equals 1 subspace of the Hilbert space. And it's proportional because I didn't try to normalize it. It will be normalized by 2 to the number of sites. And why do we say that this is a strong to weak symmetry breaking state? That requires a little longer discussion. But let me first state a couple of facts about this state. Okay? First, you can go and calculate two-point function of all the parameter in the state, and you'll find it's 0 for any, actually not just for z, for any local operator. The two-point function for z, it's 0. For other operators, it's factorized. Okay? There's no long-range order. And well, I guess I'm jumping ahead, but so in order to really define the long-range order in this state, there's something going on in this state to capture this incoherent condensation. One way to formalize it is to think about how similar the state is with another state obtained by inserting 2 charges somewhere. Okay. So to have this symmetry breaking, it means that these 2 states should be very similar. Okay. So, and that's definitely the case in this idealized state when we have a kind of superposition, a mixture of all possible charge configurations. It doesn't really matter whether you insert another pair of charge or not. Okay? But in general, we can try to quantify how similar these 2 states are. All right, so here's the formal definition. Well, it's given in terms of this quantity called fidelity between 2 quantum states, 2 density matrices, rho and sigma, and it takes this form. Okay, so it's just a definition of fidelity. So given any 2 states, I can define fidelity. If it's 1, it means the 2 states are exactly the same. If it's 0, it means the 2 states are supported on orthogonal spaces, so they are like the maximally different. Okay. And it's between 0 and 1, so it quantifies how similar these 2 states are. And here, the definition is we'll define this correlation function. It's not the usual correlation function, so we call it fidelity correlator. If you have this fidelity correlator between rho and this other state obtained by inserting some symmetry charges at two different locations. And if that correlator goes to a constant independent of x and y when these 2 points are far, this is kind of mimicking the usual definition of long-range order, then we say the state has strong to weak symmetry breaking. Now, you may ask, why do we choose fidelity in particular? Because there are other notions of similarities between quantum states. I can name a few others. Okay, and the reason, and we believe they're all equivalent, but the particular reason that we choose fidelity is because this theorem we can prove for fidelity. The theorem establishes the strong to weak symmetry breaking as a robust quantum many-body phenomenon, a phase, indicator of a phase. So the statement is the following. So if you start from a density matrix, which has strong to weak symmetry breaking, okay, and you apply a symmetric finite depth quantum channel to this state, and the resulting state will have strong to symmetry, weak to symmetry breaking. So you cannot destroy a strong to weak symmetry breaking by applying a symmetric finite depth channel. So if you start from something that has this property, it's going to remain no matter what you do, as long as you preserve the symmetry. And what you do means applying some quantum channel. And that means we do have this strong to weak symmetry breaking as a phenomenon that's universal throughout the phase diagram. Okay? You cannot destroy it.
Still have strong symmetry.
It still has strong symmetry globally, but locally it doesn't have strong symmetry.
So what symmetry is broken?
So the strong symmetry is broken to only a weak one in the following sense. So if you just take a local subsystem of the state, then you don't have strong symmetry anymore. You only have weak symmetry. Global is strongly symmetric.
Even though globally it's a mixed state.
Global is a mixed state, but it can have a strong symmetry. Right. Okay, so this is the most important reason that we choose fidelity as a definition of strong to weak symmetry breaking. Okay. All right, so with this definition, let's now look at some examples. So one example is thermal state. Okay. Yes.
Oh, sure. No, I was just wondering, you use in your stability theorem, you point out finite depth circuit, and you've been careful to point out quasi-local everywhere else.
Yes, so right. So I think I've deliberately hiding the statement for quasi-local because we only managed to prove a weaker result for quasi-local circuit. I'll come back to this point. That's enough for the purpose of establishing, for example, phase diagram in certain examples. But the case of quasi-local, the bound is not as strong as finite depth case. Okay, right? Yeah.
Evaluated at the fixed system size, or is there some notion of thermodynamic limit?
Yeah. Okay. So I should probably have put another limit in front or limited after this. That no, we take the thermodynamic limit, and then you first take a thermodynamic limit, and then take this to infinity. Right.
Question? Can I ask a question? So you mentioned that there's some channel like depolarization or like amplitude damped to like zero state that can just destroy the order. Is there a reason that strong symmetry somehow prevents you having such kind of channel?
Yeah, so that's what the stability theorem says, right? If you want to preserve the strong symmetry, you cannot have a channel that just takes a state to a trivial one. So the depolarization channel would break the strong symmetry, or the swap channel.
Even like decay into a symmetric state, that's also.
Sorry, can you say it again?
So you can have amplitude damping, like damp to zero state, or damp. If you damp to a symmetric state, I would naively believe that symmetric means like pure state that preserve the symmetry.
Right.
That as a density matrix also preserve the strong symmetry.
So
somehow this kind of channel also break the strong.
So the amplitude damping channel include a partial trace, and that partial trace breaks the strong symmetry to only one.
oh, yes. Oh, okay. Indeed, a difficult question was. Yeah. All right. Let me now move. Oh, there was another question.
The operator O, it's charged under
It's not charged under the symmetry. It's all dependent. Yeah. All right. So let's now consider example of strong to weak symmetry breaking in a thermal state. I might need to speed up a little bit. So we talk about canonical ensemble and grand canonical ensemble as examples of density matrices with strong and weak symmetries. But we also know from, again, the STEMAC that when it comes to thermodynamics or whatever local properties you want to compute, it shouldn't make any difference using canonical or grand canonical ensembles. Okay. So that statement leads to a conjecture that a canonical ensemble of a local Hamiltonian H, canonical means you preserve the global symmetry strongly, actually has to spontaneously break the strong symmetry. Now, here I didn't say spontaneously broken to what. So because we could have a strong symmetry just broken to nothing, but the strong symmetry has to be broken. That's our conjecture. And we can test it in examples. So we can say that the strong symmetry, breaking of strong symmetry is a universal feature of thermal states. Okay? It has to have some breaking of strong symmetry. And at least has to have strong to weak symmetry breaking. So any kind of thermalization has to make this happen. All right, now let me move on to another example. So this is now a non-thermal kind of example of non-thermal mixed states. So the example is very simple. You start from essentially a product state where every side, so this is an example of qubits, Ising spins, and every side has x equals 1 to begin with. So I literally have a product state of x equals 1. And this state obviously has a strong symmetry. It has eigenvalue 1 under x. Okay. Now we subject this system to a quantum channel. And what this quantum channel does is to essentially create pair of charges on neighboring sites with some probability. Okay. So this is an expression of that quantum channel. And it's parameterized by a parameter p that just tells you what's the probability of doing that. What's the probability of creating two Z2 charges, flipping two spins on neighboring sites. Okay, so now we have a quantum channel acting on the state. Starting from this pure product state, we can apply this quantum channel and we get some mixed state as a function of p. And we can study this state as a function of p, and we can study what's a phase diagram. Okay. So the claim is that there's a phase transition, again in some quote, where there are two different phases, two distinct phases. So there's some number pc, which is 0.1, and if you think about this, the p extends only to 1/2. Beyond 1/2, it's related to 1 related to 1 minus p by unitary. So we can just study this from 0 to 1/2. So there's some transition at a finite pc. Okay. And we know what happens at these 2 points. At p equals 0, it's a product state, a pure state. At p equals 1/2, actually you can check that we get this 1 plus x state. And we can calculate the fidelity correlator. This justifies why I draw this phase diagram, that in the phase with p smaller than pc, the fidelity correlator decays exponentially with the separation of the 2 points. And when you go to p greater than pc, it approaches a constant when the 2 points are far away. Okay? So there's a sharp transition indicated by the asymptotic behavior of the fidelity correlator. All right. It should decay algebraically at the power law, at the critical point. Okay, but now if I want to say that there are two phases, well, no, let's look at the definition of phase. The definition of phase is given in terms of a two-way connectedness by quantum channels. Okay? So if I want to claim there are two different phases here, then I need 3 facts. I need to establish 3 facts. One of them is I cannot two-way connect a state with p greater than pc to a state with p smaller than pc. I should not be able to do this. Okay? And then this direction is very easy. This is just messing up the state, right? Decoherent more and more. The direction going to smaller p is more difficult. This is a state of kind of cleaning up the mass. And we know if you want to clean up the mass, you need to do some work. You need to recover the pure quantum state. So the non-trivial question is whether we can recover here. Whether we can recover a p smaller than pc state from a p greater than a pc state. The other direction is trivial. So, and that's where we actually need a stability theorem in the with a quasi-local adjective in front. It turns out that even with a weaker bound, it covers this case. Okay? So one can show that using stability theorem that there's no channel to connect p greater than pc to p smaller than pc. Okay? So there's no way to connect these two in this direction. And that shows, well, that's the first thing we need. The second thing we need is that we also want to show that within one phase, say p greater than pc, I should be able to connect any 2 points in 2 directions. I should be able to go forward by messing up the state, and I should be able to kind of going back by recovering the state. Okay. And and we do have these channels, and these channels should preserve the symmetry, right? They should preserve the strong symmetry. Okay, so we do have these channels. We can explicitly construct them using the path recovery map. I'm not going to discuss the details. Okay, suffice to say that it is actually quite subtle, but we can construct these states. We can construct these recovery channels. So this establishes a phase diagram. We do have these 2 distinct phases in the sense that I defined earlier. Okay, and this is an example of 2 different phases in the world of mixed states, separated by some sort of transition. Okay. All right, so now let me say a couple more words about this phase diagram. So observables, in quote, because the fidelity correlator is not the usual observable, but if you try to calculate the observable, it turns out that they are mapped to some correlation functions or some quantities in the 2D random bound Ising model along the Nishimori line. And you might wonder whether this is specific to the model that we study. It turns out that the same kind of critical theory applies even to some other deformed models, which is not entirely Pauli. Okay, there's some funny sort of operator here. So it's hinting at some sort of universality, even we don't really know the full theory under this. Maybe there's some field theory. Okay. All right, so this concludes the discussion of the strong to weak symmetry breaking, the phase diagram. Before I move on, I think it's a good point to pause to see whether there are more questions. Yeah.
What is the signature of having, say, universality class? Like,
sorry?
What is the signature? Like, you have like exponents, critical exponents, and what is?
Yeah, that would be the signature, right? So you have different microscopic realizations of the same transition, and they're governed by the same sort of universality class. Although we don't really fully understand this. It just seems like there are examples where microscopically they look very different. However, the critical theory appears to be the same. Yes.
So you mentioned like analog to the canonical ensemble and the grand canonical ensemble.
Right.
Is there any meaningful analog for the microcanonical ensemble in this picture?
Because this is all about global symmetry. So microcanonical ensemble is, the question is, in that case, what we care about is whether energy is conserved or not, right? So it's, if I am allowed to stretch it, it's a bit like asking whether the time translation symmetry is strong symmetry or not. But I don't want to take that too far. Right? So this is mostly about global symmetry. Yeah.
Since you say that, you want to identify the same phase when you have like 2-way maps, but you can always have, 1-way maps going over one. Like, and you can always end up in the trivial state from one. Do you always expect to have critical behavior as you transition across a phase boundary? Like, if I just try to decohere everything to a product state, would I expect to have critical phenomena?
Well, if you just decohere without preserving the symmetry, right, there's probably nothing critical happening. Right. So yeah, so this is very specific. I think I forgot to mention an important condition that all of this is done in 2 dimensions. This is in 2-dimension system. Okay, in 1D you would have a very different phase diagram. So yeah, so if you don't respect the symmetry at all, then there's no critical theory, there's no transition. Yeah, so you don't expect there are 2 phases. Yeah.
Some sort of like Herman Wagner type.
Well, I think this is a question that people are actually thinking about. But just to give.
There's no Herman Wagner.
Right. I didn't mention this result, but we have some argument to show that any thermal state, regardless of dimensionality, has strong to weak symmetry breaking, even when you have U1 symmetry. So it doesn't seem like there's a very general Mermin-Wignath theorem.
What is the space of states you're looking to classify using this two-way map?
So I want to consider states with 2 short-range correlations. Okay? But that's probably not enough. We probably need to put in more conditions. There are some ideas of what conditions should be put in, but this is not completely sorted out yet. Yes.
So is there a way to define a connected two-point correlator for using the finality?
Yeah, you can define it in a pretty straightforward way, generalizing what we usually mean by a connected correlator. It should diverge at the critical point. Yes.
Phase transitions not associated with the spontaneous symmetry breaking or mixed states.
Yes, it depends on how far you want to take symmetry. I mean, if we restrict to like the usual sort of symmetry, then there are definitely transitions, topological phase transitions, which are not related to symmetry breaking. But no, this is a matter of what you want to consider as symmetry. All right, I think I should probably now move on. All right, so with a strong to weak symmetry breaking, all right, so now let's come back to the Landau paradigm. Okay, so there's I think there's the idea that we can, with sufficient generalization of symmetry, we can even account for these more exotic phases, which were thought to be beyond the actual Landau paradigm. But now they could be under the umbrella of a more general Landau paradigm once we sufficiently generalize the notion of global symmetry. So I'm sure you'll hear more about this from Schuchen and Xie. But there are many different generalizations. So there are these higher form symmetry, there's non-invertible symmetry, there's subsystem symmetry, and you can make whatever combinations between these adjectives. Now, and another aspect of the generalization that we are learning that there are more to the notion of symmetry. Usually we just say, okay, there's Z2 symmetry and Z2 is a group structure. But there's more to symmetry than just a group. And really the useful lesson that we need to think about higher structures, more subtle structures hiding in the defects of global symmetry. Okay. So I'm not going to really discuss what the details of this higher structure, but suffice to say that at least we have to think about anomaly. Global symmetry is associated with a Tooft anomaly. Okay. And in one sentence, Tooft anomaly is obstruction to having a completely trivial state that preserves the global symmetry. Okay, so I'm going to discuss 2 examples, which can be, both of them can be sort of categorized as strong to weak symmetry breaking of some anomalous generalized symmetry, to show that if you think about strong to weak symmetry breaking of these anomalous symmetries, we get interesting many-body states, mixed states, which are, and they don't have any counterparts in some sense in pure states. Okay. All right. So these are kind of the, roughly what the 2 examples are. One of them in 1D, coming from anomalous Z2 symmetry, and the other ones in 2 dimensions from anomalous one-form symmetry. All right. So I don't have to go through both of them. So but again, feel free to interrupt me. Okay, so let me talk about this example in 1D. Okay. So this is the anomaly-free Z2 symmetry in 1 dimensions. If you have a chain of spin 1/2 or qubits, then the anomaly-free Z2 symmetry is just a product of poly X, a spin flip. Okay. Now, we can make anomalous Z2 symmetry by multiplying this spin flip with a bunch of phase vectors in the Z basis. These are the control Z. These are the control Z gates acting on neighboring sites. Multiply all of them. And I'm assuming that the system is always periodic on a ring. So now you can prove that under that condition, this is a Z2 symmetry. Okay. So roughly what happens that you flip all the spins, but then adding some phase vectors depending on the spin configuration. Okay, so I'll just claim that this is anomalous. This is anomalous. No, this was first discussed in this paper by Levy and Gu on the boundary of a 2D symmetry protected topological phase. Okay, but let's just take it as, as given we have a system with anomalous Z2 symmetry, and we can also form a strong to weak symmetry breaking state under this anomalous Z2 symmetry. So just generalizing 1 plus X, now we have 1 plus U. U is this anomalous Z2 symmetry generator. Okay? So it's projecting to the subspace where U is 1. That's all it does. Now this state, again, is completely featureless. If you calculate correlation functions, they look just boring as it can be. Okay? You don't see any feature in observables. However, unlike 1 plus X, rho plus this state, 1 plus U, is actually not equivalent in this sense of two-way connectedness to a previous state. And here's a rough argument. If this state can be created from some pure state, trivial state, the psi, the trivial state, by a quasi-local quantum channel, then as I mentioned earlier, you can push a strong symmetry through a quantum channel, preserving all of its nice properties like anomaly. Okay? So that would mean that we can define some symmetry U tilde, which is not exactly as U, but no, it has the same anomaly and everything. And the product state, the trivial state, has to be invariant under this U tilde. We know that's impossible. This anomaly means that you cannot have such a trivial state. Therefore, this quantum channel does not exist. Okay? So if you want to prepare this rho plus from some pure state, it has to be a somewhat state, somewhat interesting state like a symmetry breaking state or a critical state. Okay? It cannot be a product state. So this simple argument shows that this state is at least different from a trivial product state, belongs to a different phase. Okay? In fact, we can make it even stronger that rho plus is not just inequivalent to a product state, it's inequivalent in this two-way connectedness sense to any pure state. Okay? So it's really intrinsically mixed. So to see why this is the case, I need to discuss a property, a kind of information theoretical property of the state. It's called separability. So the idea that if you have a product state, if I have a trivial state, then I can factorize the state over different parts of the system. I can write it as a product up to some local unitary, up to a product of states on different parts of the system. Okay? So that's a notion of separability for pure state. There's a generalization of that notion to mixed state. Basically, let's take two bipartite separability as an example. If I divide the system into two parts, and I'll say that rho is bipartite separable if I can write it as a convex sum of states, the tensor products of states on A and B. Okay? So that's what I mean by bipartite separability, so bipartite separable states. Obviously, you can define it for any number of partitions. So I can do it for tripartite A, B, and C, and it means that the state can be written as a convex sum of tensor products of states on each subsystem. Okay, so here's the theorem, a fact, an interesting fact about the state is that this state is bipartite separable, meaning that if you cut the system into two parts, you can write it in this form. However, it's not tripartite separable. If you try to cut it further, it's not going to work. Okay? And the intuition behind this theorem is that if you try to cut it into two parts, I can try to first cut it into two parts and then cut one of them into two again, then I would have I would have tripartite separable state. However, if you try to cut it into two parts, you can do that, but then each of them on each subsystem looks like a long-range correlated state, which cannot be divided further. Okay? And I should say that the tripartition is a tripartite refers to this particular partition of the system, not arbitrary partition, A, B, C, which are adjacent to each other and make the entire system, obviously. Okay. So this is a funny property. If you think about this for pure states, these two things are related. If you have a state that is bipartite separable for any cut, then it's also tripartite separable for pure states. However, for mixed state, we have an example now, which is bipartite separable, but not tripartite separable. That's not possible for pure states. So essentially, this is why the state is intrinsically mixed. It's not connected by two-way quantum channel to any pure states. And well, there's a stronger statement that not only it's not tripartite separable, it cannot be prepared from any tripartite separable state via a local quantum channel. So again, the fact that it's tripartite inseparable is really a property of a phase, not just a fine-tuned property of a state. All right, so we have this interesting state in one dimension that looks like a topological state, right? It has short-range correlation and it's featureless if you just look at the ordinary observables, but it shows funny properties if you think about separability, and at least we can say that it's definitely not equivalent to a trivial state. Okay. All right, so this is one example. Any questions?
Question?
Yeah.
Can it be distinguished by some kind of a bulk or boundary response function? Can it be distinguished by some kind of a boundary theory of response functions?
Boundary theory, yeah. So there's some feature if you try to define the state on an open interval. Okay, so there's something you can say when you try to make this state on an open line. There's some correlation. Response theory, I'm not sure, because even though I define this state using a global symmetry, right? I start from a system with anomalous Z2 symmetry, and I make this state by projecting to a subspace. None of these properties actually depends on the Z2 symmetry. None of these channels has to preserve the Z2 symmetry. So we use that symmetry to define a state, but then we don't really need to preserve that symmetry. So I'm not sure whether there's any response that we can talk about to global symmetry. Okay, so this is one example. Now let me move on to the next one, which is now in one dimension higher, in 2+1 dimensions. Okay. So there's a large number of results or beliefs, the well-motivated conjectures about what pure state topological phases look like in 2+1 dimensions. And there's even a classification that that's strongly believed. Okay, I'm not going to really explain these words, but there's a nice mathematical object that classifies topological order states in 2+1 dimensions, essentially in terms of universal properties of the anionic excitations. Okay, up to some invertible states. Okay, and then there's also a kind of generalized symmetry perspective on these topological order states in 2+1, which that we can think of them as spontaneously breaking the generalized one-form symmetry. Okay. All right, so now to define the example, I'd like to first quickly review Tori code, which probably you have seen too many times. But let me just state what this is. So this is there's a standard Tori code model where you have qubits on the edge of a square lattice. Okay, so X and Z are the Pauli operators. And we have these two terms in the Hamiltonian, product of X around a vertex and product of Z around a plaquette. Okay. You sum over all of them. And this is a commuting projector model. All the terms commute. So we can solve the model completely and understand excitations and ground state excitations, and figure out whatever detail of this model that you like. And this is a gapped system because of the commuting projector. It's a gapped system. And excitations can be classified into 3 types. They can be kind of decomposed into 3 types. One of them is what's called the E-anion, which is a violation of this red term, the product of X. And the other, I think the red one is a violation of the blue term. And the E-excitation is a violation of the red term, which can be created by applying some string operators along some path that connects the two points. Okay. And you can make a bound state of E and M, and this would be a fermionic particle. So this is the famous Torrey-Cote model. Okay, so we can also think about the model from the symmetry perspective. So instead of thinking about excitation, we think about the symmetry of the ground state. And here I use a one-form symmetry in a non-topological way. So I don't demand the one-form symmetries to be topological operators. Okay. And the 2 terms in the Hamiltonian are basically generators of the one-form symmetry. So one of them is the product of X operator along a path on the dual lattice, and the other one is a product of Z along a path on the lattice. Okay, now, before I talk about this interesting state, let me first consider a state that is not terribly interesting, but illustrates the process that we're going to use to kind of create that state. So this is a very classic model of noise in this Torrey-Cote model that we turn on a bit flip noise. Okay? So it's a quantum channel whose cross operator are Pauli X on each edges. And then we can just multiply all of them and apply it to the state. Okay, again, it's parameterized by a probability of applying that cross operator X. So you can study it as a function of P. Okay, so we get this phase diagram. Again, this is actually the same phase diagram that we saw earlier because it's actually Kramer-Wanier dual to the model that we discussed for the Ising strong to weak symmetry breaking. Okay. But in any case, there are again 2 phases. One of them is non-trivial in the sense that it's all connected to this P equals 0 pure Torrey-Cote state. They belong to the same phase. And the other one is kind of connected to the P equals 1/2 point, which you can show is a trivial state. Okay? So this trivial phase here and non-trivial phase. Okay. Now, we can also look at the phase diagram from a symmetry perspective. So over here, the state, so the channel explicit break the strong E one-form symmetry. Okay. I guess I didn't define the strong one-form symmetry, but you can imagine how it's defined. Over here, we have emergent Z2 cross Z2 one-form symmetry, which is anomalous, just inherits the same anomaly from the ground state of Torrey-Cote. And this symmetry is spontaneously broken, so that's one way to think about the topological order in this region of phase diagram. Now, on the other side of phase diagram, we still have an emergent Z2 one-form symmetry, but it's not free, and it undergoes a strong to weak symmetry breaking, which can be made more precise, but I'm not going to do that. Okay, and at the P equals 1/2 point is generated by this product of X operator. Okay, so how do we visualize these states? So one way to visualize states is to think about it in terms of the M excitations, because applying the X operator, we flip the plaquette terms. So that creates excitations on plaquettes, which are the M anions. Okay. So here I'm contrasting 2 kind of condensations. One of them is a coherent condensation of M anions, which means we simply make a coherent superposition of states with M anions populated in all possible ways. And if you just look at this state, stare at it for some time, you realize it's a product state. Okay. Now, here, what happens at P equals 1/2 is that we are incoherently proliferating M anions by making convex sum of states with M excitations populated somewhere in all possible ways. Okay. So that's an incoherent proliferation. So that's a representative state in the trivial side of phase diagram. Okay, so this model was used to study the loss of quantum memory, and we can learn a lot about mixed state phases from this model. But now let me tweak this model a little bit. So there are three anyons, E, M, and the fermion in toric code. E and M, they are more or less the same. I mean, not actually the same, but they are not very different. The fermion is very different because it's a fermion. The other two particles are bosons. So bosons can condense. You can make this coherent proliferation of bosons, but we cannot make a coherent proliferation of fermions. They cannot condense in the usual way. Okay? However, there's nothing stops us from making an incoherent proliferation of the fermions, simply because we are making these convex sums, and the convex sum doesn't care about the phase vectors you get from exchanging fermions. Okay? So we can make this state. At least there's no obstruction of writing down the state. Okay? All right, so let me now actually make the state by writing down a similar model, starting from the torical ground state and turn on a local channel to create that state which is a convex sum of fermion populated torical states. Okay. And the details are not terribly important. We can write down some local cross operators and make this quantum channel. And there's a similar phase diagram. But instead of non-trivial and trivial phase, I'd like to claim that now there are two phases, both are non-trivial. So this one is connected to toric code. It's basically the same as toric code. The other one is distinct phase, which is still non-trivial. It cannot be connected to a trivial phase. Okay. How do we see that? Well, one way to see that this is non-trivial is again through the lens of symmetry. So we can ask, what's the global symmetry, one-form symmetry on this side of the phase diagram? And it's easiest to see it at the p = 1/2 point, where we can write down exactly the density metrics. And it's invariant under this particular one-form symmetry. So I draw an example of this one-form symmetry, which is a product of x along the dual path and the product of z's along the lattice path. It looks complicated. But the point is that this is actually distinct from just the product x and product z, because if you compute the anomaly of this one-form symmetry, which is really the same as the statistic of anyons, this is a string operator that creates fermions. So the one-form symmetry has anomaly. It's a Z to one-form symmetry with anomaly, and the anomaly is represented by the fermionic statistics of the open ends of this string operator. Okay. So it's still anomalous. This is not bosonic. This is anomalous one-form symmetry. And it's an emergent symmetry of this phase. Okay. So this is distinct from any one-form symmetry that one would encounter in the pure state in the bosonic system. So you cannot have this one-form symmetry in the gapped state in the bosonic system. So this is an example of intrinsically mixed state in that sense. I just said that you cannot find this one-form symmetry in a gapped ground state in the bosonic system. Okay. So this is a very curious state. I know some of you are in the audience are thinking about this state. It's a beautiful state that I don't feel like we understand very well enough. Okay. All right. So I think it's time to conclude. I guess I'll just skip this. So here's the summary. So strong and weak symmetries help sort of anchor our understanding of mixed states. And we discussed that the strong to weak symmetry breaking is a robust many-body phenomenon in mixed states. And if we think about anomalous symmetries, they lead to examples of interesting many-body mixed states, which can be thought of as like the analog of topological order states. Okay, so thanks for your attention.
Thanks for a nice talk. So there's one part in the very early part of the slides where you were talking about the two-way channels, right? And there's also the statement that if you are in different phase, basically you cannot do this two-way. Right? So now, if you are in the same phase, why can I not take the second channel to be just the path recovery of the first one? Is it because you're going to include in the same phase?
Why can I not take the
channel to the other state, but why would the other channel not be just the path recovery of this other one?
Yes, of course, you can do path recovery of any channel, but it's not guaranteed. I mean, generally, it's not a local channel, right? So we want both channels to be quasi-local, right? So you can do path recovery, but in general, it will be a very non-local channel. So you can do local recovery, but then there's the issue of whether you can actually make global consistency. Yeah.
Is there a field theory for strong to weak symmetry break?
I think this, I don't know the answer, but there are recent works from Jianhao and other people that study hydrodynamics as a field series for U1 strong to weak symmetry breaking.
Yeah, actually, I think for example, let's consider U1 symmetry. Xiaoyang and I have a work that the strong to weak SSB of U1 symmetry just imply emergent hydrodynamics, especially the diffusive hydrodynamics. And we then claim that the diffusive hydrodynamics is actually pretty much like a Goldstone mode of the U1 strong to weak SSB. Right. Yeah, the paper will be appeared tonight.
Question in the back.
Can we use the topological entanglement entropy to detect the phase transition in the
Yeah, so no, you can study topological entanglement entropy, although maybe it's better to study topological mutual information or something that's more pertaining to mixed state like topological activity. They will show some interesting behavior across the transition. And the other questions, again, I think that still puzzles many of us is what to say about topological activity in this fermionic cohiratory state. Right, but one can definitely study these quantities for mixed states. Yes.
A state for any like premodular category in a similar way?
Yeah, so I had a slide which I skipped. So thanks for asking that question. Yes. So yeah, in short, we can construct a mixed state which has any premodular category as a strong symmetry. Okay, so there's systematic construction of that kind of states. Right.
Yeah. For the pure state, there's a requirement that the pure state is a ground state of certain local Hamiltonian. Here you construct a lot of mixed state. Right. Whether those mixed states should have some similar. I worry about if construct arbitrary mixed states. It's quite well, just like if you construct arbitrary pure states, it's very well.
Yeah. So we definitely want
condition.
We definitely want to have some sort of notion of locality in the state. The correlation functions should have local behavior, although that's probably not enough. And the other requirement they can think about is like, we want to be able to physically prepare the state from, for example, the ground state of some Hamiltonian, local Hamiltonian. So maybe you want consider state that can be reached from the Hamiltonian in some efficient way.
All the mixed state you consider can be prepared from products via quantum channel. So quantum channel without
not all the mixed states can be prepared from product state by quantum channel, but they can all be prepared from the ground state of some Hamiltonian, local Hamiltonian, by then applying some quantum channel. So that's all examples can be prepared this way.
Can we define strong weak symmetry breaking by introducing symmetry breaking external field and taking the thermodynamic limit and then taking the field to zero? Yeah, which is a usual way erase the closed
explicitly, and then yeah, I think there's a way to define strong to weak symmetry breaking in this manner. Like we study how the state behaves if you just measure the system, but the measurement actually breaks the symmetry from strong to weak. Then it should collapse the state to only has weak symmetry. So there's some notion of, there's some statement that we can make along that line.
For these two-way channels, is the important constraint on the channels that there should be some kind of Z product from down? Or is that where the quasi locality is coming from? I mean, you just want to ensure some Lee Robinson, and that's the main condition.
You mean Lieber Robinson for Lindeblad or?
Yeah, I mean, for instance, if you wanted to consider.
Yeah, I guess we know if you have a local Lindeblad, you would expect some sort of Lieber Robinson bound. Although I guess I didn't really make it very clear, but you can try to capture that sort of locality properties through some other properties like correlation functions, or maybe certain entanglement measure should behave reasonably.
So in one of the examples, you use the Kramer-Swann duality argument. Do you expect Kramer-Swann dualities to hold for both strong and weak?
Sorry, which example did you use?
Was the Torah code example? And, you had like people 0.109. You said, oh, that's the same as the I thing.
Yeah. So I just made the statement that this phase diagram is the Kramer-Swann dual of that phase diagram of the Ising, decoherent Ising model.
The arguments can always be used for strong symmetries. I guess I'm concerned for strong symmetry, you're kind of restricted to a symmetry sector. So I don't know, you could always use some isomorphism between the Hilbert spaces.
So in that particular model, the one form symmetry that is needed to do the Kramer-Swann duality is preserved strongly. So in that particular case, you can do Kramer-Swann. Not sure that answers the question.
So you say yes in this example.
In this example?
In general.
What is true or not?
So yeah, Kramer-Swann dualities allows us to relate phase diagrams of models related by gauging. Right. I don't even know how to think of gauging strong and weak symmetries, but so is there even a notion of gauging strong and weak symmetries? Is there a notion of Kramer-Swann dualities for strong and weak symmetries?
I haven't thought about this very carefully, but I would guess that we have the strong to, the Kramer-Swann duality under gauging of a strong symmetry. The usual one is really for gauging a strong symmetry. Actually, mechanically gauging a strong symmetry.
Yes, we can continue this conversation over dinner.